So one question for the participants. Do you see all my shared display? Okay, thank you for the feedback. So welcome everybody to the second session of the Circle Virtual Summer School 2025. Yesterday we had a session about web forensics. Today it will be more the classical disk forensic stuff, but more an introduction. But not just an introduction, the goal of this session is to provide background information. Because imagine you do a forensic analysis, you present your results, and somebody asks, how do you come to these results? Today, with using all those very good advanced tools, at the end you will say, oh, the tool told so. And the idea of this training is to show how the tools come to the results. Yes. And with this knowledge, you do much better understand the results, and you understand what could be the limits of the tools. So my goal is to show you what the data told, not what the tool told. So you should be able to read the data on low level, on bits and bytes level, and to apply data structures to it, and read the data with a hex editor. So really working with low-level tools. So this is the goal of this session. And before we start, I will make a small demonstration where I show that tools can fail. So I have a USB stick. I will connect this USB stick now to my PC. Okay, here we go. So on the USB stick, we have 3 files, test 1, test 2, test 3. Let's open them. Okay, they open in a different window. But now you see on these 3 files, we have 3 little different ASCII art. So very straightforward. Okay, now I connect the USB stick to my Windows machine. So it's disconnected from the Linux machine. It's now on the Windows. Okay, it's mounted. We see 3 text files. Test 1, 2, 3. And now let's look into them. And we have 3 text files with totally different content. So that's a little bit strange, isn't it? So we have 3 test files. On Linux, they have different content than they have on the Windows machine. Okay, let's connect back to Linux. Here we are back. And we have our ASCII art back. Okay, this is a little bit strange. So the USB stick behaves different on 2 different operating systems. This is now usually a good idea to start a forensic investigation on the USB stick. So I take my command line and I increase the font. So let's check what happens if I connect the USB stick to my Linux machine. First, I remove it because now I enter the command message thw. Okay, let's connect it back. So our dmask tool shows us clearly, okay, we have a disk SDA with a partition SDA1 on it. Okay, let's test. Let's see how it is mounted. So we see our partition SDA1 is mounted on my Linux machine. We can check with another very simple command line tool, fdisk -l dev SDA. Yes, and the fdisk tools shows us, yes, there is a partition somewhere on the disk. Here we have the start sector, the end sector, and it is 57 megabyte. So it's a small disk. Now let's do some more tests. Yes, let's, for example, take a tool from the sleuth kit, the forensic toolkit, and I do the same. I list the partition table, mmls dev SDA. Oh, that's strange. The forensic tool, sleuth kit, the mmls command from the forensic tool says, it could not found, it did not found a partition table. So you have a tool, a forensic tool, which says something different than your Linux tool. Okay, let's do another test. Use fs.stat. This is a tool to read file system information. And the other tool tells us there is a file system on the USB stick, starting at the first sector. So we have totally strange behavior and different output of different tools and different operating systems. And honestly, this happened to me. So that's why I can make the presentation. So now the goal is I will show you how to be able to understand the bytes on the USB stick to figure out what's going on. And we will start with real basics. So we will start with thinking about bits. What are bits? On the USB stick, the data is stored in bits. So there's a stream of bits starting at the beginning and ending somewhere. But if you take a look on this slide here on this bit stream, do you really are able to say what is the meaning behind? No, of course not, because these are more or less zeros and one without any structure. So you cannot use this information. You cannot use these bits to get information out of it. So you must put some meaningful way to these bits. And we often start with putting it in groups. Yes, for example, we put 8 bits in groups of 1 byte. That's on the bottom of the slide. You see how those data are rearranged in bytes, and we put some addressing to it. So we have already much more information because we have addresses where the bytes are stored, and then we have the byte value itself. But it's far away from the end. Let's take a look at the next slide. Because we can arrange byte on different, we can arrange bits on different way. Yes, we can put them in bytes, or we can even put them in words too, which means we put 16 bits in one word, or we make double words with 32 bits, and so on and so on. So we have many different possibilities to group them. And you have many different possibilities to interpret the data, the bits inside those groups of bits. Yes, is it an integer? Is it big endian, little endian? Is it a floating point number? Or is it an ASCII value? Or is it even binary data? And you need to know all this information to be able to read the data and then make information out of it. So before we go further, just a small excursus in numbering systems. We, as a human, work very much with the decimal system. And as we see, the decimal system have a structure which goes from right to left. And the most right value is the lowest value. So the 5 here in this example means this is 5 multiplied by the system, which is 10, with the power of 0. So this is 5. The 4 basically means this is a 4 multiplied with the power of, with the 10 with the power of 1, which means this is 40. And the 1 means this is 1 multiplied by 10 with the power of 2. So this is 100, and the same for the 2000. And this structure applies for all number systems. Yes, for the binary, we take the value, multiply it with 2 with the power of the position. And for hexadecimal, we have, again, we take the value, which in this case is, as we have not enough numbers, we must take characters. Yes, we take A for 10 until F for 15. And we multiply it with the 16 and with the position, with the power of the position. And so every number system is working. At least every number system based on our today's structures. Yes, Romanian numbers with X and B and ones and I's and M is a little bit different. But this is much more clearer and much more easier to live with. Okay, now with this information, we are able to read this byte of data because we know this is 1 multiplied by 2 with the power of 4 because it's position 0, 1, 2, 3, 4. So we know this is 16. And the same way we know this is 64. So we can calculate out of this binary number, we can easily calculate the value 80. Okay. And now we check how different numbers or interpretation of numbers work. Yes. Now we interpret it not as a normal integer number, but we interpret it as a signed integer. And the signed integer, you change this position of the bit of this bit position in the byte, and it becomes the sign. So a 0 there means it's a positive number, a 1 there means it's a negative number. So with the 0 here, we have a positive number. We still have the 80, what we already calculated before. And, and now we check for negative numbers. For a negative number, we have to put a 1 here. So let's check again back. So we have a 1 here. So this is a negative number. And we have the 16 and the 64. So now the question is, what negative number is it? Is it minus 80 or something totally different? And to calculate the negative number, we use something which is called, let me check, the complement, the two's complement of the number. So here we see an example. Yes, here we have a number. We're starting with a 1, so it's a negative number. And this is the value, the rest of the value. As a positive number, it would be 214, but it's a negative number. So how do we calculate the two's complement? The first step is we invert all single bits. So from the 0, we become a 1. From the 1, we become a 0. 1 to 0, 0 to 1, and so on and so on. The second step is to add a 1, to add 1. So how does it work? We add this one, and 1 and 1 in the binary system becomes a 0. And we have one value back here, which springs over to the next digit. So we have here a 1 and a 0, which is a 1. 0, 0 gets 0. 0, 1 gets 1. 0, 0 gets 0. And here we have a 1 as a result. So we have a 2. We have an 8 and a 32. So we have basically 42. And this is the negative number, 42. So this is how we calculated the negative number, which is interpreted as a signed integer with the two's complement. Okay, I have a small exercise for you. This is a hands-on training. So please feel welcome to do one exercise to get warm with it. Maybe you use your text editor or something simple tool to do the exercise. And now the question is, calculate this value of a signed integer number. So I give you 2 minutes of time to start a text editor and write down this number, and then I will scroll back one slide so that you have the possibility to see the how to perform it manually. And yes, feel welcome to put your output in the chat message. So I wait 1 minute, and then I will show you in real time how I would make it. Just for your information, I see there were some questions with for the slides and stuff like this. They will be published later, afterwards. So I see the first results coming in, the first questions. "48 seems to be a very warm candidate." So let's check. So first I do the bitwise flipping. 0, 1, 0, 1. And now we add 1 to this. So now we see we must go from right to left to come to the results. So 1 and 1 is 0. And we take a 1 with here. 1 and 0 and 1 is 0. And we take a 1 with over. So 1 and 0 and 1, 1, 0. So we take another 1 with here, and 1 and 0 and 1, 0. So we take the next one with here, and 1 and 0 and 0 is 1. Here we have a 1, and here we have a 0. And a 0. So we have 1, 2, 4, 8, 16 and 32. 16 and 32 is 42 is 48. So it's minus 48, the value. So all the results I saw in the chat, oh, most of them. Most of them are good. Cool. Thank you for participating. So let's see on my slides. Yes. Convert to decimal minus 48. Okay. So this is interesting. Now you can, you probably learn it at school at one time, but forgot about it. But now you can read integer and signed integer numbers again. Now we come to the next very important. No, before I have a challenge. Now that you know how those works, I have a challenge for you. Can you find the biggest and the smallest possible positive signed integer and the biggest and the smallest possible negative signed integer number? Okay, here we go. I see the first outcome, 0, -1, -128. So let's go through it. Let's start with the positive numbers because this is the easiest. So the biggest positive number, we have the 0 at the beginning because this is the need to positive. And we have the ones. And for the smallest possible positive number, we have the 0 at the beginning and the zeros afterwards. So most of you are right in the chat. The smallest possible positive number is 0, and the biggest is the 127. Now it comes a little bit more complex for the negative numbers, because we start with the 1, yes, and then the ones behind, which turns into 1. But in this case, as we know it is a negative number, it turns into -1. While the smallest negative number is -128. So the positive numbers goes from 0 to 127, and the negative numbers from -1 to -128. I'm very happy that many people comes to the good result. Yes, I see the question in the chat. So basically 0 is classified as a positive number because it starts not with a 1. And so 0 is the first positive number, and that's why it only goes to 127. Because we have 128 positive and 128 negative numbers. Quite cool. Okay, now we come to the next very important topic. No, first a small excursus again. Because at the moment we are working with binary information, binary data, but at one point it would make sense to make them more compressed because they are really large, to make them more compressed and change them into hexadecimal numbers. So basically this is very easy. I will show you how quick you can convert binary and hexadecimal numbers because they all based on a 2 factor. So they are like sisters and brothers. It's much more hard to convert it into decimal numbers because the systems are not so close to each other. So as you see here in the slide, you can easily convert 4 bits in the byte in one hexadecimal number. Yes, so it's very easy. Yes, you can convert. You see 1, 2, 4, 8. 8 is the hexadecimal number of the value. 1, 2, 5, 4, 4, and 1 is 5, so we have 5. 0, F, A is 10, so we have 1, 2, 4, 8, 10. Somebody like to record. The recording will also be published afterwards. So you don't need to record it. It will be recorded. And we have the 1, 2, 4, 6, 4, 2, 4 and 2 is 6. So we have immediately the hexadecimal value. So you see, it is very easy to convert. Let's do the same for the lower row, and you see how quick it will go. So we have 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1. So here we have 1, 2, 4, 8, 10. So it's a 9. Here we have 6. Here we have A, because this is 10. And here we have a 5, 0, F. 12 is A, B, C, and a tree. So you see how quick you can switch between hexadecimal and binary data. Let's take a look at the next slide, if I was correct. Looks good. And with the hexadecimal data, we have basically the same information, but it is much more compressed. That's a very big advantage. Okay, now we came to a very important topic, and you may remember the terms, but don't remember exactly what was the difference. So big endian and little endian. This came into place if you have values which cover more than 1 byte. Yes, for example, if you have the value 258, it's not possible to illustrate it with 8-bit. You need 2 byte. Yes, you need 16-bit to replace this value, to present this value. And here we see it again. If you like to have the value 256, we have 0 times 1, 0 times 2, 4, 8, 16, 32, 64, 128, 0 times, but we have 1 time 256. So we need 2 byte to store this information. So we need a word to store this information. And what we see here on the top, this is how we as human read those data. Yes, if it is stored in the memory, you have one memory place where you have the big value and then followed by the next memory place, which stores the lower bits of the value. This is how we human are used to read the information. But for computer, it is an advantage if they switch the byte. So the internal bit order is always kept the same, but the position of the bytes switch. So to represent this 256 in little endian representation, you write first the lowest level bits, the lowest level byte, followed by the high level byte. And this is the little endian representation. And this is very important to know about this because this system is still used on so many places. I know it was back in 1988 or something like this when Intel CPUs used this little endian representation, while Motorola CPUs used the big endian representation. Let's take an example. And let's work a little bit with hexadecimal values because it's more easy, you get the information on a smaller place. So imagine you have, this is a little endian word in your memory or on your disk. 1 byte 96 and the next byte A5. But it is little endian. And now you have to get the value out of it. So how do you proceed? You have to flip the byte. Yes, the last byte becomes, with the lowest value, becomes here. And the byte with the highest value comes here on the second position. And now we can calculate the value. So we have, let's take a calculator. So we have basically here the low value. So this is a 5 multiplied by 16 power 0. So this is a 5 plus 10 multiplied with 16 power 1. So this is a 10 multiplied with 16 plus, and now we have to take this value, 6 multiplied with 16 multiplied with 16 plus 9 multiplied with 16 multiplied with 16 multiplied with 16. Oh, fine. Okay, I got a different value than I have on my slide. Let's check what the calculator do. 6A, 96A5, okay, converted to decimal. So my online activity was good, but what is on the slide is bad. I have to fix this error. But you see, this is the lowest level byte, and this is the highest level byte. And this is called little endian. No, why do make it so complicated? It is easier for the computer to calculate with this order of bytes. Because imagine, this is in the address before this address. If you check how the computer, how you calculate, yes, if you calculate 22 plus 99, so you have to add 9 plus 2. So you start at the right. You start at the right side. So you add 9 to 2. So you have basically 1 and 1 over here. So you have 12. 12. So you see, you start at the right digit. You cannot start here at the beginning with the high value. You need to start with the low value. And now if you look here how the memory, how the data is stored in memory, the computer read this address first. Then he have to save this value somewhere else. Then he read this address, and then he start working with this value and store it in between, continue working with this value, and then put the results together. This is complicated. And in early days of computer was slow and memory was expensive. So it is much more easier to change the byte order and to first start working with the little values. And you can immediately read the byte, you continue working with the value, and then you take the next byte and continue working with the next value. So it's more hard for human, but much more easier for computer to work with this order. And this system is used everywhere. Yes, it is used in the master boot record. It is even used in the GPT and the GUID partition table. It is used left and right in the registry, on all kind of file systems. It is used everywhere. Okay, let's make it a little bit more complicated. Yes, now we have 4 bytes inside one value. So we have a double word. And now I will show you how to apply those conversation into little endian with more bytes. So we take first the highest value byte. This should become the low in the last position. Then we take the second byte, and this should become in the second last position. And then we take this byte, which becomes the second, and at the end, the last byte with the lowest value becomes the first byte. So now you see the computer read this information in little endian and can immediately start working with this data one after each other. And I think I have no, I have no exercise for you, or possible. Bye. So this is how numbers could be stored on disk, in memory, anywhere. Yes, and you need to know, is it an integer? Is it an assigned integer? Do we take 1 byte? Do we take 2 bytes? Or do we take 4 bytes? Is it big endian or is it little endian? So with this information, we can understand what are the values behind. And here I show you how the big endian data, or how human read data and how this computer maybe store the data. Now I will make a small exercise live for you, where you have to convert the other way around. So I will give you a 4 byte little endian number, and you have to calculate the value out of it. I will put it here in my notepad. I don't have it in the slide. So take. So imagine you get the bytes and you read in the specification, these bytes are in little endian format. I will not make it too complicated. So I hope this is good readable. So now imagine you get something to analyze. You get these bytes, and you know these bytes are stored in little endian order. Now you have to calculate the value out of it. That's your exercise now. So I will wait 3 or 4 minutes. I see there's already one answer. So one answer in the chat. Ah, da comes in other answers. Fantastic. So many answers are correct, it seems. Some are very close, maybe just a small typo somewhere. So let's go through the solution. So this is the byte with the lowest value. It comes at the beginning. Then we take byte number 2, which comes now on place 2. And the byte with the highest value move onto the byte with the lowest value. So this is little endian value on the computer, and now this is the big endian value working for us humans. Okay, let's put this in the calculator. And convert it to decimal. And yes, many, many correct answers in the chat. And I'm sure the others, they was very close. There's just one typo somewhere. Okay, so we saw how to read the integers, the signed integers, positive, negative, how to reorder bytes from big endian to little endian and from little endian to big endian and get value out of it. That's already a good base. But there's also the possibility that data is interpreted different. Yes, it could also be that we have ASCII value. So the value in the byte means not a number, or not directly a number, of course, it is a number, but this number is mapped to a character. Yes. Here, for example, we have these bits which turn into 0 hexadecimal, which is 112 in decimal. And then you need a ASCII table to look up that the 112 or the hexadecimal 70 turns into a P. And the same with the next byte, the PING, so a ping. So if you read the data, you need to know what data is it. Is it a number or is it ASCII or binary data or whatever? Okay, now we come to the next step. Take a look at this bit sequence. Can you read it? Can you get information out of it? Can you generate knowledge out of it? I know it's unfair from my side. Of course not. So now let's see how to bring structure into this. So first, we converted from binary into hexadecimal and apply addressing to it. So here we start at byte 0 and we have 64, 65 byte of information. So we already have a little structure inside. Okay, now let's continue. We need a definition. Yes, we need a definition to understand what is the meaning of this bytes. So we need a data structure, for example. And yes, here we have a data structure. This is a data structure which do not exist somewhere. I just put it in place. And I call it the DFEA, the Digital Forensic Edu Archive. And in this data structure description, we get information. What is the meaning of the bytes? On which position? So let's take a look in the definition. So we have offset 0. We have here is offset 0. So starting with this byte, we have a header signature, DFEA, for Digital Forensic Edu Archive. So this is ASCII, as described in the definition. So we have 4 bytes of ASCII, which should be DFEA. Then on the next offset on byte position 5, which is offset 4. So we are 1, 2, 3, 4, 5. So we are here. At offset 4, we have one length, 1 byte, which tell us the length of the file name. So basically the Digital Forensic Edu Archive is something like a tar ball, where you put many files into one file. So this is just a very simple format for the educational reason. So here this byte, according to the definition, tell us how long is the file name of this file inside those archive. And you see the value at this place. And so you get the file name. Then on the next byte position, we have 2 bytes of information, how much data are inside this file in the archive. And this structure is stored in little endian format. The next byte at offset 7 is 1 byte inside, and it tells us what is the data inside this file. Yes, if it is a -1, it's an ASCII data. And if it is a 0, we have base 64 encoded data. So until here, the information is clearly fixed. We have a clearly structure at which offset we have can expect which information. But now it comes a little bit, oh no, the next offset is good. At offset 8, now we have the file name. This is still fixed. At offset 8, we have the file name, but the file name itself is of a variable length. So it could be 1 character, 2, 4, 8, 16, 127 characters, because we can take 1 byte to tell the length of the file name. So the length of the file name starts at position 8, but it is not clear how long it is, because we have to read this information out of this information. So this is variable. And then somewhere later, after the file name, we have the data, which is either ASCII or base 64 encoded, and which have amount of some bytes, and the amount of bytes of the data is stored in this 2 bytes starting at position 5. And this structure repeats for each file which is stored inside those archive. And then at one point we came to the data FF, which means this is the end of the archive. So no more data are expected. Okay, now I'll show you step by step how to apply this data. So first we take the header signature. We know this is the header signature. It should be DFEA, which is 44, 46, 45, 41, hexadecimal representation. Then the next byte, we know here we have the length of the file name. Here we know we have the length of the data, and here we have what kind of data. Is it ASCII or whatever? And then, okay, let's go on. We can read those from an ASCII table. We see it is DFEA. So this is indeed the header of the first file in the archive. Then we can read the next value, which gives us the size of the file name. So the size of the file name is 8. So the file name has 8 characters. Then we read the data, the size of the data itself. And now we see we came to 14. And this 2 bytes is a signed integer, as far as I can read. No, it's a little endian integer. A little endian integer. So this 0E00 get converted for us to make it readable into 000E. And 000E is 14. And we learned before how to switch data stored in little endian on the data structure, how to switch it in human readable. Then we have the next byte, which is the type of the data. And this is a signed integer, FF. And we can switch back to see what is FF. FF we have here, and it's a -1. So here we have a -1, which means the data should be expected to be ASCII data. And now it's easy. We have 14 bytes of ASCII data, which is the content of the file. So we need an ASCII table. And we know it goes from here to here. Then we need an ASCII table and can read, watch the file name, sorry. And can read the file name because it's test.txt. So we know the file name is 14 byte. It goes from here to here. And then we can take an ASCII table, convert it, the values into ASCII, and we have test.txt. And we know because the file name is 14 byte, it stops here. And the next data are now the content of the file, which is 14 bytes. So 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So here we have the data of the file. And the data of the file is ASCII encoded. So we need again simple ASCII table to read the content of the file, which is hello world. And we have a carrier return at the end. So you see with the bytes, with the information, with the hexadecimal values, and with the data structure, now we are able to make sense out of this bits we saw at the beginning. And this is important because if you can do this manually, if you have a tool which reported strange output, then you maybe make progress and came to the conclusion and to a good result. So I feel I get a little bit tired. I propose we make a small pause of 15 minutes. And then we came back and continue. Okay? So now we have 15:05, so we came back at 15:20. See you later. So everybody's still awake? Okay, so let's continue. So let's recap where we are at the moment. So I show you how to read different kind of data and bring them in order, and how to read data structure and apply it on the data. A small reminder, why do we do all of this? Maybe be reminded to the exercise we did at the beginning of the demo, where I put a USB stick into a Linux machine and have test files with ASCII art. Then I put the same USB stick into a Windows machine, and we have files with different content. And I run several tools on the USB stick, and the tools also provide contradicting output. So basically, with the tools, we are not able to solve the question, what's going on here? So, and this is the goal of this training, to show you how to read the data manually, to at the end resolve questions like this. So, okay, you was very happy. You are all awake, I saw in the reaction, because now you have to do an exercise. And especially we have here those digital forensic edu archive format where we can put several files in to an archive. We have the data structure of the archive, and we have the bytes inside the archive. And I show how to resolve the question, what is the first file? What is the name of the file? What is the content of the file? What is the file, the size of the file name, and so on and so on, the size of the data. And now you see here is a second file inside this archive. And now it's your test, your exercise to try to resolve as much as possible from this second file. So let's the exercise begin. It's your turn. So if you find any information out of the file, then I will now start monitoring the chat. You can put some information in the chat. Yes, and basically you have to start over with the second file, which starts here, and do what we did before with the first file with the name test.txt. So basically you need to read the data, interpret the data. Maybe you like to look online for an ASCII table to be able to convert ASCII data, for example, for the file name. And you have to apply one little endian to big endian conversation, and you have to read one signed integer. I will give you still some time, and maybe in 5 minutes or the like, I will start showing how to resolve step by step. So I see there are first information coming in. Looks quite cool. Yes, there are many good feedback, good information coming back. So let's take a look on the solution. So the first thing is to read the data again from offset 0, which is now here. We have now here the offset 0. So here we have basically our next header symbol. You see the bytes are absolutely the same. So we have our header signature that the next file begins. So the next integer value tells us how long is the file name. With 7. So the next value tells us how much data we have inside the file. So we have 1100, which is little endian. So this turns into 0011, which is basically, this is 16 as it is hexadecimal, and this is a 1, so we have 17. Cool. Very good. Very good. Some people solved the complete challenge. Okay, then we have a 2. No. We have 1 byte at offset 7, which is a signed integer. So offset 7, 0, 1, 3, 4, 5, 6, 7. We have the signed integer. It's a positive number because the first bit is 0. So the value is 0. If you check back in the definition of the data structure, it means the content is base 64 encoded. Yeah. So 0 means the content is base64 encoded. And if we take an ASCII table, we will find the name of the file. So this is dot 6 and 4. And here I will copy paste the information extracted by people and no, put in the chat. Looks quite okay. This is a carrier return. Okay, now the question is, what is this strange content? We know it's base64. And now we like to convert this content into normal. So, and the base64 is no black magic. It's an encoding scheme. And it's still used very often. For example, emails encode binary data into base64 so that it will move through all the mail servers without any kind of issue. So it's quite common to encode data in base64. And we can use a tool on the command line to convert it back into readable data. So we can echo the content and pipe it to the base64 tool with the switch decrypt or decode better. It's not encryption, it's decoding, encoding. And we see, yes, the content is DFIR rules. There's another tool which can be used to convert the data. Search it. Maybe you hear about it. Yes, it's the tool CyberChef, which is online, and it's on GitHub.io, and it's based on JavaScript, and so everything is run on your own computer. You don't put information online with this tool. So, and this tool converts data into, it converts data. So we take our string and then we try to make base64. To base64 or from base64, we have base64 data and like to get them in clear text. So you see, we have now here our output, the clear text. So quite useful tool to make tons of conversation. So let's check if I have the same output on my slides. Yes, I have the same output on my slides. So we have a second file in our archive, and we was now able to read the length of the file name, to read the length of the data, to understand that it is base64 data, convert the file name from ASCII into ASCII, and convert the content of the data into base64 data, and then decode those base64 data into plain text. And what we see next is the end of file signature. That means now we should not expect any additional data. The tool, the file is finished. So each tool which read the file or ourselves should know, okay, there are no more data expected. We only had 2 files in our archive. So, now we see how we convert a sequence of bits. We apply some addressing to it. We group it in bytes and larger units like words. We put some interpretation rules inside it, apply integer encoding, apply signed integer, convert little endian into big endian, and at the end we end up with information. And now in forensics, it is also important where do you find those information. Yes, do you find something, for example, in the command line history? Do you find it in the browser history, in the registry, in the autorun folders, or inside a binary in the temp folder? And so at one point you came from plain data to information and to knowledge. So, and now I came back to the solution of our initial challenge. What happens with this USB stick? As we see, tools are not helpful. They will not solve the issue. But I can show you what's going on with this USB stick. That's now the solution. So imagine you take a USB stick and connect it to a Windows computer. Then it is basically handled like old times floppy disk. Yes. If it is empty. If it is totally wiped, there are no bytes on it, it is empty, you connect the USB stick to the Windows computer, what will happen? A window will pop up and ask you, do you like to format the device? And if you click yes, you can choose the file system and the cluster size, for example, and then he starts formatting it. And what does this mean under Windows? Like you see illustration here in the ASCII art at the bottom, Windows will put something which is called a volume boot record in the first sector of the disk. So another name which is known from earlier days is a boot sector. So Windows will put a volume boot record, or the other name boot sector, into the first sector of the disk, and then create the file system afterwards. And then you can store on the rest of the disk, you can store your files. This is how Windows handle the point when you connect a totally empty USB stick to the Windows machine. So the very interesting thing here is the boot sector, the first 512 bytes on the disk. Now we will look into this 512 bytes. This is how it looks. So on the one hand, you have your sequence of bits, here represented in hexadecimal numbers, and in the hex viewer also represented, converted to, if possible, readable ASCII. And there is a definition what should be in which position at the boot sector. Yes, for example, here we have from byte 0 to byte 2, we have a jump to bootstrap code. So this 3 bytes, this 3 bytes, and this 3 bytes is an assembler instruction. And if you try to boot your computer with this USB stick, it will execute this assembler instruction. It will jump somewhere here and display the text. This is not a bootable disk. Please insert a bootable floppy. This will be executed when you try to boot the computer with this not bootable disk. Then you have some other information. Yes, you have here some so-called OME ID information. You have the information that it is an NTFS file system. You have the information bytes per sector. So this is at position 1B to 1C. So 1. Oh, back. It's a small error. It should be B to C. So here we have B, we have C. So we have 0, 0, 0, B, and this is bytes per sector. 0, 0, 0, B, and this is, again, little endian. So you have to apply the conversation from here, little endian, to big endian. And then we have 512. So we have 512 bytes per sector. Then in the next value, we have 0.8, and this value means we have sectors per cluster. So it's just a one byte size, but you understand the idea. You can, if you have the data structure and you have the data, you can read the data manually. What is important for our exercise with the USB stick here is that you have maybe 200 bytes used for the volume boot record, for the boot sector. You have more or less roughly 200 bytes used. The other 300 bytes are more or less empty. They are not used. Just here at the end, we have something which is called the signature, and we have this basically in every boot record. This is a kind of a signature that the boot record ends there. But important for our exercise, the first 200 bytes are used to define the boot sector, and then it's empty. Now let's see how we handle a USB stick with a Linux machine. Usually in Linux, when you create, when you have a very empty, absolute empty USB stick, you first create a partition table. Yes, you say, I have partition 1, or I have 2 partition, or here in this example, you see the illustration. We have 3 partitions on the USB stick. And very important, the first sector on the disk is not a boot sector. It's a master boot record. And the most important information in the master boot record is where on the disk do partition start and where on the disk do partition end. So this is called the partition table. So you see the difference. The one system starts with a boot sector, which describing the file system. And with this system, with the master boot record, the first sector say, where do the first partition start, where do it end? Where do the second partition start, where do it end? And so on. And then on the partition itself, so on the partition. You format the partition then. So on the partition, you create the boot sector, and then you store your data on the file system inside the partition. Now let's take a look on the master boot record, how it looks on with a hex viewer. So you have some bytes in used here at the end of the partition. This is the partition table. The partition table stays here, and for each partition we have 16 bytes of information. And here we have the second partition table entry starting for the second partition ending here. Here we have the third ending here, and here we have the fourth ending here. So with the classical master boot record, you only had the possibility to define 4 partitions on one disk. And here again, the values are clearly defined. For example, this 07 tells the computer that there is an NTFS partition on this partition. On this first partition on the disk, we have an NTFS partition. And then we have this value, 4 bytes, which tells the computer where on the disk, on which sector do the partition starts. And this is little endian, so you need to be able to convert it to become readable. And here we have the second value, which tells the computer where do the partition ends. And again, this is little endian value. Okay, and you have to convert it to make it readable. Here we start with the second partition table entry, and this is basically empty. Yes, this is empty. So this is a disk with only one partition table. And now we can try the test. Okay. We like to read this value manually. So we want to know where do the partitions start. So we have 8032, 8032 to 022. So this is where the partition starts, and this is little endian. So to make it readable, we have to change it. So this is easy. We open our calculator. Where that's calculator. Here we go. We have hexadecimal value. And now we like to read it human. So 1440. And I'm not sure if I use in this slide the real boot record I had from my USB stick, or if I use another USB stick. But we will see. We will make. Okay, the MML tool do not work. Fdisk will maybe also not work, as it is not a disk. Yes, it works. Ah, wonderful. And you see the value we calculated out of the data exactly fits what do the tool tell us. So in this tool fdisk tell us, yes, here we start like we calculated it now manually, and here it ends. And the other tool, MMLS, tells us there is no partition. I don't know. It's not something I can read. And now we can also calculate check the end of the partition. We came to the same result. So we have 80 CD 0100, turn it into human readable 001 CD 80. Convert it into decimal and compare it with the output of the tool. And it's exactly what we calculated. So that's basically the idea of this training, to make you capable of do this, what the tools do automatically, to do it manually and resolve the problems. And now I show you what is the difference. If you make a USB stick with Windows, you have those one partition of the complete device. And if you create a master boot record with partition table on Linux, you have a totally different structure. And now here in our example, we have a mixture of both. Yes, so we have a kind of a polyglot boot record. So we have a mixture of both. We have the NTFS information from the boot sector at the beginning of the sector on the USB stick. And as you remember, the boot sector stores information at the beginning of the sector and the rest is empty. And then if you scroll down, so here you have the boot sector information. If you scroll down, you have a partition table in this boot record. So you have both the information, and as you remember, for the master boot record, the partition table is at the end of the disk and the beginning of the, at the end of the boot record, and the beginning of the boot record is empty. So you have a mixture. You have at the beginning of the boot of the first sector, you have the information from the boot sector. And at the end of the sector, of the first sector on the disk, you have a partition table. So you have a a mixture of both systems on one sector, in the first sector. And then, so you have the Windows part with 3 files. And if you connect it to a Windows system, it will show these files. And if you connect it to a Linux system, the Linux system will ignore the boot sector and read the partition table and mount the partition somewhere on the disk where you have 3 other files, here in this example with the same name but with different content. And I made a presentation last year about this topic. We can check online, because it should be online on the Circle website. So if you like to reproduce the complete USB stick exercise, you go to the training, materials, you go to the digital forensic, and here we should have, from OSTCert Conference 2024, here you have the complete slide deck of how to create this polyglot USB stick. And Also with all the disk images. The master boot record disk image, the volume boot record disk image, and the polyglot disk image. So if you like to reproduce this exercise, here you have all the slides. But take care, because if you do this with a root, with the user account as root, you need to be root to access all the devices and modify access to devices. And being root user and working on devices can kill your device. So please do not do it with a production PC, do it with a test PC. I have a disclaimer because here I have the full exercise how to create the USB sticks, strange USB stick, and then I have slides with all the commands I used. But be sure you need to use at one point the tool DD or at two different points. And being root user and using the tool DD, you can destroy completely all the data on your disk. There's no question back, are you sure about what you are doing? When you say DD and write to my USB stick, but by accident you write to the hard drive, you will overwrite all the data on your hard drive. So take care what you are doing with DD as a root user. So now we are at the end of the presentation, a little bit too early, but that gives us time for question and answers, probably. I will check the chat. Yeah, usually I like to give this training. I put some exercises inside, but usually if I give this training physically in a class, I see if I wait for most of the people to finish the exercises, and I go to desk by desk to talk with them and discuss with them and maybe give a hint. And this is why we are now finished a little bit too early, but so I can give you back some time of your day. If I knew a USB with DD, would it be recoverable afterwards with the right tools? No, that's the point. If you use DD to write data on the USB, then the USB which was on the data which was on the USB are overwritten. So you have to interrupt DD as soon as possible, and what is not overwritten then is recoverable. It happens once to me in reality when I make a class and I detect really quite after 20 seconds that I'm writing to my SDA1, my boot disk on my Linux PC. So I interrupted immediately, and at the end no data was lost, but the complete booting part for the operating system was overwritten. So I did not shut down the computer anymore before doing a backup, and then reinstalling the operating system. It saved the system and all the data, but it can happen. So I'm quite happy that I have an NV. Uh, what's the name? Yes, an NVMe disk, because with the NVMe disk, it's not so dangerous. I overwrite the USB stick, which is usually an yes, an SDA. So that's a good protection to have an NVMe. Extra exercising. Yeah, I have, when we go back to the Circle website, there are more exercises which you can all play through. Um, because I give several presentations at Cyber Day in Luxembourg. And normally for all this the trainings, I have all the slides and the disk images online, or for most of them, and you can reproduce the exercises where I make presentation about. For example, here we have a extended boot record loop. What is this meaning? It means you remember the master boot record can only store 4 partitions. And if you like to use more partitions on a Linux system, you have to create something which is called an extended boot record, where you can put more partitions and more partitions inside. And one partition inside the extended boot reports then points to the next partition. And with the EBR loop, I create one partition boot record which points back to the beginning. So we create a loop. We had 3 partitions, but at the end there was 120 partitions mounted, because each time the same partitions get mounted in a loop. So there are some funny exercises. Here we have an exercise recovering data from a wiped disk, where somebody wiped a disk, but only half. And then there was the possibility to recover the second partition on the disk. Then some exercise with resident data, because, okay, that's something else. So there are some other exercises online. I'm curious if I once received some feedback. Did you ever see this wired file system setup in the real world? Yes, indeed, I did. I did, because I was once preparing a training with a USB stick, and then I had exactly this behavior. And I was about to say, okay, the USB stick is broken, and I will wipe it and start over from scratch. And then I thought by myself, no, moment, you are a forensic analyst. You should be able to find out what's going on here. And then, so I did the analysis manually. I understand that we had a boot record and a partition table together in one sector. And so I could recreate this USB stick now and use it for trainings and demonstration. So indeed, yes, I had it on my own. For the And Frau ME with wear leveling, I don't know exactly how it will affect this. This is a test, an experiment I like to make in the future. I have some SSD disk bought some months ago to do this test and experiment, but until now I had no time to do it. So, but it's in the pipeline to make some tests with this. But for DD, you have to understand it copies data. Yes, if you say DD data, input data, output data, it copies the data and overwrites everything which was there before. Okay, so I propose if there is no additional question, I will stop the recording and we can close the session for today and you get back 40 minutes of your daytime. So thank you all for attending, for participating the exercises. It was a real pleasure to see that people really participate. And I wish you much fun with the following sessions of the virtual summer school. So, bye-bye.